Alright, let's start out by reviewing the challenge problem from yesterday. So we need to draw the sketches to these graphs. So for this first one, I start out with a constant slope, so that means I start out with a constant velocity until time naught. So this is a sketch. You could have drawn this line up here, you could have drawn it down here. It doesn't really matter, it's a sketch. And then up here, notice if I were to draw out my tangent lines, they would be approaching 0, and they get to 0 about some point up here. You could argue that it's still slowly decreasing to 0. Anyway, it should look about something like this. And then for this graph, we start out really steeply with a very steep negative slope, which means I have a very negative acceleration. And then notice at here, my time naught, that I go from rapidly decreasing to still decreasing, but not as rapidly. So that means my acceleration is somewhat less negative. So I should have this little discontinuity there. And then for this graph, we want the change in velocity. And remember last video, we learned that the area under an acceleration versus time graph is change in velocity. So we're going to have a 1/2 times our base of 2 seconds times our height of 5 seconds there. And we have two composite shapes here, so I'm just going to find the area of each of them and add them up. So over that triangle, that gives 5 meters per second. So my velocity from 0 to 2 seconds changes by 5 meters per second. And then for this, we have a rectangle. So you would take your base times your height. And notice that this base starts out at 2 and it goes to 6 seconds. So that means my base is 6 minus 2 seconds, or 4 seconds. So we have a base of 4 times a height of 5, and that means my change in velocity of the rectangle is 20 seconds. So you just add up the area under those two shapes, and you have a change in velocity of 25 meters per second. So in this video, we're going to go over a few typical AP problems involving kinematic graphs. So first, we have an object that is going to be launched vertically from the ground. Which of the following pairs of graphs represent its velocity and acceleration versus time? So we're going to ignore air resistance, so we have a constant acceleration. In this problem, you need to think that acceleration is due to gravity, right? And if you're just throwing a ball up in the air, it's going to have the same acceleration because it's not like going to fly hundreds of meters above the surface of the earth. So it's fair to say that we have a constant acceleration and that there is going to be an acceleration, because when you throw that ball up, the ball is going to go up and then it's going to come back down. So there has to be an acceleration to slow the ball down to the top up here and then speed it back up on the way down. So graph B can be eliminated because it says we have 0 acceleration. And then graph C can also be eliminated because it says we have a changing acceleration. And if you look, the velocity and the acceleration graph are the same, and that does not follow from what we learned in the last lesson. So now we can look at our options A and our option D. This here definitely does not match this graph. If we have a positive acceleration, we should have a correspondingly changing velocity, and this here does not follow that. And that leaves us with option D. If you think about it, that makes sense. You launch the ball, it has a positive velocity. It slows down until it reaches the top, where it's 0, and then it falls back down, speeding up on its way down. And acceleration is constant that entire time. So that is the answer to our first problem. Alright. At time t equals 0, car A accelerates from rest while car B passes car A while traveling at a constant velocity. Both cars continue on parallel straight roads. Which of the following occurs at time t equals x? Select two answers. This is a possible AP question because 5 of them are multiple select with 2 correct answers, and you need to get both right. There's no partial credit for these questions. So right away, we look and we see we have a velocity versus time graph. And we know that A cannot be right. Acceleration is the slope of these graphs, and car B is traveling at a constant velocity and therefore has no acceleration. Well, the problem clearly states that car A is accelerating. So A is not one of the right answers. Car A has traveled half the distance of car B. Well, distance we know is the area under a velocity versus time graph. So if we look here, car A has this triangle and car B has a square. It appears that car A's triangle is half of car B's square, so I would say that, yeah, it's fair to say car B has traveled half the distance. Car A has traveled half the distance of car B. And if it's only traveled half the distance, that means car A is behind car B and not passing. If car A were passing car B, they would have to have these same areas under the graph, and car A would still have to be accelerating. So in this question, B and C are the correct answers. Here we have a position versus time graph of an object's motion, and we want to know at which points does the object have a positive acceleration. So we know acceleration is the slope of a velocity versus time graph, or you could say it's the second slope of a position versus time graph. So to know at which points the object has a positive acceleration, we're looking for increasing tangent lines. So if I were to do this at point A, I would see that the tangent lines to the graph get progressively steeper throughout point A. So that would tell us that point A has a positive acceleration because we're looking for upward curvature in the graph. Do this at point B, and we start out with really steep tangent lines that get progressively less steep throughout point B. So that would tell us that the graph has downward curvature and thus a negative acceleration. And point C strongly replicates point A, so we could say that point C also has a positive acceleration. At point D, we eventually reach a tangent line of 0, so we go from really steep to 0. So that tells us that point D is a point of deceleration. Point E, we start out with very negative tangent lines, and as we get past point E, they become progressively less negative. This graph has also more of an upward curvature. We go from very negative tangent lines to less negative tangent lines. So point E is also a point of positive acceleration. And then at point F, we don't have any tangent lines, so we can't say that the object has a positive acceleration here. So our points of positive acceleration are A, C, and E for this problem. This will be our last practice problem for this video, and it's a little bit trickier. We want to know at which of the following times does this object have the greatest velocity, and we're looking at an acceleration versus time graph. Most people are immediately tempted to pick W because you see you have a positive acceleration, and then after that it decreases and then it's negative, so the greatest velocity can't be below this axis, and you're right, Y and Z are not candidates. But you need to remember that the area underneath an acceleration versus time graph is the change in velocity. So if we were to look at the area up through point W, we have that triangle, but if you look at the area up to point X, you have a much larger change in velocity, and it's above this time axis, so it's positive. So even though acceleration is decreasing between points W and X, it is still positive. The object is still speeding up, just not as rapidly as it was earlier. So X is when you have the greatest velocity. Now for part 2, we want to know at which of the following times is the object farthest from the origin. Based on part 1, maybe now you're also tempted to pick X, but we need to look a little bit closer at this graph. So we go from a positive acceleration to a negative acceleration of the same magnitude. So that means that we have the same changes in velocity, it's just that this one down here is negative. So that means we have a change in velocity of 0. And because these are the same magnitudes, we never have a negative velocity because we're never going backwards past the origin. And that means at point Z here, the object is farthest from the origin. Maybe to clarify a little bit more, because this can be a little bit hard to grasp, we are saying that these are equally spaced intervals. So basically, in this first part, from time t equals 0 to time t equals x, the object is accelerating positively and its velocity is increasing over this entire interval. The acceleration is positive throughout this entire interval. However, once we reach point x and we start going downwards, the object is still having a positive velocity. However, we have a negative acceleration, so it's moving forward, but it's slowing down. And because these changes in velocity are the same, because we have equally spaced intervals and we fluctuate between this positive acceleration, this negative acceleration, the change in velocity here is the same as the change in velocity up here. So here the object is speeding up, and then over here it's slowing down to reach a change in velocity of 0 once you look at these areas. And that means that if the change in velocity is 0 and we're traveling forward the entire time, by the time we reach point Z, this object is going to be the farthest from the origin. For today's challenge problem, I'd like you to sketch a graph, just an outline of what this would look like. You don't need to scale the axes, of a dog's position versus time in a park. So we're going to call the initial emotion of the dog to be positive. So this dog is walking in the positive direction at a constant speed when it suddenly sees a squirrel and rapidly speeds up. Before slowing down, stopping, and sitting a short while, it then turns around and walks back to where it began at a slower speed than its initial walking speed. So I'm just going to add a little positive here. Positive speed for the initial part. Alright, good luck, and that concludes this video.